Good afternoon, doctor. My name is Li Changhe, and today I will present my analytical lab project titled Leverage Machine Learning to Predict Salary Level in the Data Science Field. My speech consists of 6 parts. Let's begin with the object. With the rapid development of data science, the demand for related positions in various industries has risen, and the salary level varies significantly due to a variety of factors. This study used the Kaggle dataset and 6 machine learning models to predict salaries in the field of data science, evaluate their performance, and identify key influence factors. Using machine learning to build an intelligent salary prediction model can help improve the scientificity and personalization of salary decisions. The part 2 is a problem statement. Current salary forecasting methods are mostly based on static historical data, lacking real-time and personalization, and are difficult to couple with the rapidly changing job market needs. To solve this, I developed machine learning models to predict salary more accurately using real-world job data. The part 3 of the object. This study aimed to explore the data characteristics of the dataset, build and compare the predictive performance of 6 machine learning regression models, identify the key features that affect salary, and provide salary predictions and career development recommendations based on the option model. The part 4 is methodology. The most important thing in this study is the methodology. It includes 4 aspects. Among them, data pre-processing is particularly important. Our dataset came from Kaggle and includes 742 data and 42 variables from 2021. Data cleaning included cleaning up useless values, missing values, and outliers. After cleaning and selecting features using feature-wise, I reduced the variable from 42 to 15. When encoding features, there are 2 methods. For ordered variables, I use mapping encoding. For objective variables, I use target encoding. Finally, the data was standardized and divided into train and test sets in a ratio of 80-20. The next is the model building. I use 6 regression models: linear regressions, decision trees, random forest, nearest neighborhoods, support vector regressions, and multi-layer perceptual. These models span from interpretable to complex, covering a wide model spectrum. At the same time, I evaluate them using 3 metrics. MAE is mean absolute error. It measures the average magnitude of errors in predictions. With lower the values indicate better performance. RMSE is root mean squared error. IMSE is sensitive to large errors and provides a measure of average magnitude of predicted errors. R-square it indicates how well the model explains the variability of the data, with value closer to 1 being better. Okay, the part 5 is discussion. The following table shows the results of drawing these six models. The random forest regression achieved the best overall performance because it has the lowest RMSE value of 10.26 and the highest R-square value of 0.899. For easier understanding, I have displayed their scores in figure. R-squared is arranged in descending order, while RMSE and MAE are arranged in ascending order. We can from the we can we can know the descent tree was closer to the random forest, but slightly overfit. MLP and linear regression performed moderately, moderately well, while SVR and KN did not generalize well on the data set. This is this is followed by an explanation of the models. Camping model is a random forest regression. Random forest has the lowest IMSE value and the highest R-squared score, achieving the best overall performance in both metrics, except the MEA is slightly lower than the descent tree. It strikes a good balance between retaining interpretability and accuracy. Random forest has outstanding performance for the following reasons: anti-overfitting ability, non-linear interaction modeling ability, feature importance estimation, scalability, and efficiency. All algorithm summary include three aspects: the diversity of six models, including linear, tree-based, uh, distance-based, kernel-based, and neural network, ensure the coverage of various computational and interpretation features, make it possible to conduct a comprehensive comparison in terms of interpretability, flexibility, training time, and performance, thereby achieving a robust cross-algorithm comparison. Finally, is the conclusion part. First, we face the limitations. This study has small sample size, and the future availability is not very comprehensive, such as lack of features like bonus or benefits. The use of target encoding for categorical variables may cause certain bias. In future studies, I recommend use broader datasets, adding more detailed features, and finally turning advanced models. To conclude, this project proves that machine learning, especially ensemble models like random forest, can provide highly accurate and practical salary predictions. It's useful not only for job skills, but also for HR departments and recruitment platforms. That's all. Thank you for listening.